I will first start from today. I will talk about little bit about linear stability analysis, because I found it that it will be very helpful for the later of the course to know little bit of linear stability analysis. So we already see it, but let me first introduce some concept of nonlinear dynamics. So suppose you have an equation ddt of x is equal to some function of fx. So it means, suppose the x is the, now for the case, suppose x is the position, or you may, x is any kind of variable, it could take any value. So this means that x is changing, this means x is changing with time t, and the rate of changing is actually depend on fx. Now this is called a dynamical equation. Now for studying the dynamical equation, if I write a dynamical equation, it doesn't tell anything about the system. It only tells about the system at any point x, what is the velocity of the system, what is the rate of change of that state of the system. Now if I want to ask whether or not we can tell something about the system, I want to know if I know, let us assume that if I know the state at t equal to 0, could I tell the where the system will go at any time t equal to, this is our goal. But in but for nonlinear equation you will always find, so this xt, a closed form solution of xt, is not possible, not possible for all equation. Now what can we what could we do at best? So maybe we don't know that intermediate state. Could we know that where the where our fixed point, where our where our system will go at time t tends to infinity, means if I wait for enough longer time, where my system will go. Now that is, can we know, means could we in principle determine where the system is at limit t tends to infinity, maybe at some x star. Now that x star should have, means should possess some property. One of them property is that, that means if I if I reach at point x star, the system will not move further, that means system will stop there. That means if suppose this is my space, this is my state space x. Now since I in general I cannot tell what the intermediate what the state at the intermediate time, we want to know what will be the state at infinite time step. So suppose, so I am telling that it, suppose that it is going at infinite step at x star. So at x star it should possess one property, that at x star, when it reaches at x star, it will not change further. So that means
But I have a query here, that quite possible that the system may be oscillating kind of the system or the periodic kind of the system.
okay.
Then at X star, it may not be possible that system reaches to a fixed state kind of thing.
Yeah, that also I will cover here. Wait a little. So this means I want to know, x, is there exist a x star where if the system reaches, if I by brute force if I take the system there, it may happen. So means could it happen that here after reaching this point there will be no change further. That means is there is a x star for which ddt of x at x star becomes 0. That means in this point the velocity is 0. Is it possible? Let's find that. So that means dx dt means f of x at x star should be 0. That means if I can solve this equation, f of x star is 0, then I will get in principle a solution for x star, which will be, means it is a fashion of writing. but nothing to do it. Means we can, in principle, it simply says that in principle we can solve this equation, and I will get a point where the velocity is 0. Now now I know that there is in principle uh, point. Now I want to check this condition. So I am asking whether or not the trajectory is going toward this point x star, or it is, it may be there, two cases may happen. So one of the cases, yes, I know that there is a point, if system somehow reaches there it will stop and it will remain there forever. Now is this state is achievable or not? Achievable means if suppose at some time step my system is in this state or in this state, will the velocity in this state will go toward this direction, or velocity will be, means velocity will be from this point in this direction. For the case 1 we know, means for the case 1 we can tell that if the velocity is in this fashion, then at some point of time it will go toward this fixed point, and after hitting this point, since after hitting this point there will be no velocity, so it will be there forever. So this kind of situation is called stable fixed point. And the second kind of fixed point, it says that if I remain at very close to the fixed point, it will always go from that fixed point, go far away from the fixed point. This kind of fixed point is called unstable fixed point. This is stable. This is stable fixed point and unstable fixed point. Now how can we see that whether a fixed point is stable or not? Let uh, means, is it clear until now? Is it clear?
Yes, and except that point
Huh.
wherein you wrote that x star is equal to f inverse 0.
Okay.
So that point is not clear.
Okay. Oh, let me, means this is only a solution. Suppose fx is some kind of equation of x. Suppose ax square or axn plus b x to the power n minus 1 and is 0, then in principle we can solve this x, this polynomial equation, and we get a solution for this x. And in mathematics there is a, it is a general language, how can you write this x in terms of f? It is called the inverse function, inverse function of this. So nothing to do with the solution, it is only a fashion of writing. So that's it.
Okay, okay.
Huh.
So does this mean that 0 in fact is not the solution of this? I mean, if I put the value of x is equal to 0 in this polynomial,
Huh.
it is true that I will get, I mean, this might be a solution,
Huh.
I'm not sure, may not be a solution. So what this f inverse 0 indicates that there
Okay.
exists some solution or 0 is a solution.
No, there exists some solution, there exists some solution. Suppose there exists a solution, you always find some solution for which this equation will be, since it's a one dimensional equation, you will get, for if it is n dimensional, means its polynomials n, you will get n solution. X equal to 0 may be a solution of this equation or may not.
Okay, okay.
But let me not write in this way at all. So I will say that there will be a set x star, capital X star, which contain all the points x star 1 star x2 star, all the points for which this equation will be satisfied. So
Okay, but then what is the relation in between satisfying a equation and reaching to the point x star? Because x star is the point at the infinite.
no, there is a relation, so that I am coming, means that point I am coming. So until now we know that if a system is in this point, it will stay forever in this point. That point is clear. So now I am trying to convince you that uh, how I am, how I can assure that at time tends to infinity it will converge to to that point.
Okay, 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 okay. Fine, I understood. And
Huh.
that is why you wrote this, the first case as a stable
Huh.
one, wherein the everything, I mean, from the vicinity of this x
Huh.
star, you are moving towards x star.
Yes.
And second one is the unstable one, wherein from the vicinity of the x star, you are moving away from the x star.
Exactly. Exactly.
Okay. Yes, thanks.
Okay. Then.
Joy, I have one question.
Okay.
So, when you are writing this picture at
Hmm.
t to the t tends to infinity, it
Hmm.
is some kind of boundary conditions you are putting, or
No, no.
it's
I'm not.
just
I'm not putting
I
here.
just missed it, the
Okay. Okay.
initial part.
No worry. So this is not a boundary condition I am putting. I am saying, so in general I have a nonlinear equation. Now, as a theorist, I uh, want to see the future of the state. So I want to solve the equation. In principle, I want to write a closed form solution. If you tell me any time, if I know the initial position, and if you tell me a time, I should run my means my solution should give the exact xt where the system actually reaches. So that is my goal. But in principle, you means for nonlinear equation, there is not a closed form solution existed for every nonlinear equation. Now then, what we can means why we can ask for best. So can we means by analyzing this equation, would we know anything about, we know the intermediate time where the system will go, but is it possible to know where the system will go at t tends to infinity, means if I wait long enough, where the system will go, what is the future of the system if I wait long enough. So that is captured by this and that I am asking. Is it clear?
Yeah, it's clear, but I then my next question will be, then why are you putting that
Hmm.
there is no change? Is this something that is related to the fixed point that
Yeah,
you're
yeah,
saying that?
exactly, exactly. I am saying that these points should be such a way that after getting there, since I am saying that this is my the future state, so after hitting that point, it should be remain there. It just astray from that point. I will say no. My future state is not that. If I long enough, my system will be something else. If it hit that point, it should remain there. For means it should not move from that point.
Yeah, yeah. Some kind of a termination state where it
It is
just
in,
stays there
yeah,
forever.
exactly, you can say terminated state, but exactly in nonlinear dynamics the technical term for this point is fixed point, where the dynamics remain fixed for infinite time, so it is called fixed point.
Okay, thank
Okay.
you.
So then let me see these two situation. So because this is a my fixed point x star. Okay. Now suppose I am in the vicinity of here. So this is the distance x star, and suppose this is an infinite small distance epsilon. Now this will be x plus epsilon. Now I want to see my equation, how my equation behave around this point. Let's see. So in place of x I have to write x star plus epsilon d dt of x star plus epsilon and equal to f of x star plus epsilon, where epsilon tends to 0. Now,
So what is x and what is x star here in this diagram?
okay,
I mean, both are
a,
same, is it?
x is my the state of the system, and x star is my the fixed point where the velocity stops.
In this diagram, I mean,
Yeah.
both values seems to be constant.
Huh?
In this diagram, I mean, where is x and where is x star? Because when you
Okay.
wrote, I mean, this red point is x star plus
Okay.
epsilon.
I
Okay.
uh, it is
Yes, yes.
then it will be d sin x star is constant. This will be d epsilon, and this will be if I, since epsilon is very small, we can expand it by Taylor series expansion. It will be epsilon d d dx of f of x at x star and many other terms. and which will be contains the nonlinear exponent of the epsilon. I am saying that since epsilon is tends to 0, so that's why I can neglect in principle all the higher order terms. So it contains all the epsilon square terms. Now this equation will be d epsilon dt, and we know at the fixed point f velocity is 0, that means f x star is 0. So this equation is d epsilon d dx of f of x at x star. Now since derivative at x star is some constant, say this constant is lambda equal to d dx of f of x at x star. So this equation will d epsilon dt will be epsilon lambda. Now you see that if if lambda is greater than 0, since epsilon is greater than 0, epsilon is this much distance is epsilon, so epsilon is always greater than 0. Now if since epsilon greater than 0 and if lambda will be greater than 0, then I can say d epsilon dt will be always greater than 0. So that means when time increases, my epsilon will be increased. So that means my velocity will be in this direction. So in this point, the system will move in this direction. So in this direction, my velocity will be moved. Now if it goes in this direction, then I can say my fixed point will not be achieved by the system, because the system will move in the other direction of where the fixed point is. So then I can say if the lambda is comes out to greater than 0, then I will say if lambda greater than 0, then I will say the x star is unstable fixed point. Okay, and you can solve this equation exactly. So it will come out as epsilon equal to some epsilon 0 e to the power lambda t. So if lambda is greater than 0, epsilon will increase, that means velocity is in this direction, my system will always go far away, move away from the fixed point. Now if it is other case, second case, that if is lambda is less than 0, that means dx of fx at x star is less than 0, then my equation will be dx epsilon lambda. Since epsilon greater than 0 and lambda is less than 0, that means d epsilon dt is less than 0. So that means my epsilon will decrease as time increases. So then I will say if this is my fixed point, so this is x star. Now this is my distance epsilon. Now I will say my system, since d epsilon dt is decreasing with time, so that means epsilon is decreasing with time, so my system will move in this direction, and at some point it will asymptotically reach to this x star point, and when it will reach it, the velocity will change and the system will remain there forever. So we can say in this system that for this system, the if uh, lambda is less than 0, the x star is stable fixed point. Is it clear?
Yes.
Okay, then as you are saying that how we can get the orbit, let me do that here. Suppose in there is a equation similar to that. I have two dimensional equation. One is dx dt equal to some f of x, one is dy dt equal to some g of x. Now here also my system will be in two dimensional space. Now let me, in one dimensional the visualization is easy, so here two dimension. When the I will say my system will not, sorry, this will be, I think, This is a function of xy, this will be function of xy. So when my system, I will say my system will achieve a fixed point when the both the velocity will be 0 at this point. So that means my fixed point, definition of a fixed point will be if x equal to x star and y is equal to y star is fixed point, then I will say if x star comma y star equal to 0 and g x star comma y star equal to 0. So if the system has some fixed point, then this fixed point will automatically satisfy these two equation, or other way around, if means uh, I will solve these two equation, I will solve these two equation and I will get a fixed point in two dimensional space. And it is the meaning of the fixed point is same if the system reach that point or attain that point, it will not change further anymore. Now let me do the same thing again here. Now here, if you do the same thing, you will get x star plus in epsilon x, means since it is two dimension, so suppose here is a point, let me, this is my x, this is my y, so this is y star, this is my x star. So this point will be y star plus epsilon y, and these points will be x star plus epsilon x, and here epsilon x and epsilon y are tends to 0, these are very small. So if I in two dimensional space, if I remain very close to this point, my fixed point, what the system will do, what the dynamics is telling me. So let's check that. So we'll do again the linear stability analysis. So let go there. So we have to check dx dt will be f of x star plus epsilon x and y star plus epsilon y, dy star plus epsilon y dt is g of x star plus epsilon x comma y star plus epsilon y. Now again, if I expand these two linearly, I will get this term dx star, sorry, d epsilon x dt will be f of x star y star plus epsilon x ddx, and I am ignoring the second order term of epsilon x square and epsilon y square. So ddx of f of x at x star comma y star plus epsilon y ddy of g x star y star plus other term which I am ignoring. So there will be epsilon y dt, this will be g of x star y star epsilon x ddx of g x star y star epsilon y df of dy x star y star. Sorry, this should be f and this should be g. Is it clear up to now? This is a standard Taylor series expansion.
Yes, but then why did you introduce two separate things, say f of xy and then g of xy?
Oh, because
So can you?
because velocity of x direction and y direction, it need not be same. It maybe this is a case that where these two direction velocity is same, but we will always means it need not be the na. So x directional velocity and y directional velocity may not be the same. I mean, for if you consider for a projectile motion, if you consider means I'm not getting your point. Why means you are asking
Yes,
why?
yes. Now I understood,
Okay,
because I was under the impression that as if you would be taking the partial derivative with respect to,
okay,
say, yeah, x, and then with respect to y kind of the thing, to observe the change in the x direction and
and
then
y
y
direction.
direction.
Exactly, exactly. Now this will be now my equation will be d epsilon x dt will be epsilon x some constant. This will be not right in this way. Okay, okay. Let me write in this way. D del x. Yeah, this should be del x. Exactly. This should be the partial derivative. Del x f at x star y star plus epsilon y del f del y at x star y star. Since these two terms are 0, definition from the fixed point, epsilon x g x x star y star plus epsilon y, so del y y star. Now this is the equation. Uh, now I want to see, means it again it's a linear equation, but the equation is quite cumbersome. So now I want to transform my space xy direction in a way that these become linearized. So let me write in this way. So this equation, suppose epsilon equal to epsilon x and epsilon y a column vector, then I can write d dt of epsilon will be uh, d dt of epsilon will be del f del x, and it is at the point of x star y star, del f del y del g del x and del g del y at x star y star, and this will be epsilon x epsilon y, right? So this will be my equation. So this will be my equation. Now I can change my variable in a way that I can write in principle, means I, if I diagonalize this matrix, I will get, I will, means diagonalize means I will transform my uh, uh, my space in such a way that these will become diagonalized. So then my equation will become, suppose my diagonalized eigenvector is something like epsilon tilde x and epsilon y tilde. Then uh, then we can write the equation in terms of this: epsilon x tilde dt is actually lambda 1 epsilon x tilde, and d epsilon y tilde dtt is equal to lambda 2 epsilon y tilde. And let me tell you what is the epsilon x and epsilon y. So epsilon x and epsilon y will be, this is the matrix. Now if I diagonalize it, so I will get two eigenvector and two eigen values corresponding to those eigenvector. So this epsilon x and epsilon y is nothing but the eigenvectors of this matrix A, and lambda 1 and lambda 2 are the eigenvalues corresponding to this matrix. How you can calculate this eigenvector? We don't have to care about what is the exact form of the epsilon x, but since we want to know about the future state of the trajectories, we want to know the eigen values only. How you calculate the eigenvalues? Simply by solving this equation: minus lambda del f del y and del g del y del f del g del x minus lambda at x star y star equal to x star equal to 0. If we solve the equation that will give from this determinant, so it will be del f del x minus lambda into del g del x minus lambda minus del g del y and del f del y is equal to 0. If I solve this equation, I will get two values of lambda. One is lambda 1, one is lambda 2. Now if both lambda 1 and lambda 2 is less than 0, then I can say that the solution of the equation is x tilde will be epsilon 0 tilde e to the power minus e to the power plus lambda 1 t, and epsilon y tilde equal to epsilon y 0 tilde e to the power lambda 2t. Now if lambda 1, both lambda 1 and lambda 2 is less than 0, we can say that that the distance between these 2 points actually decreasing and decreasing to 0, since epsilon tilde x and epsilon tilde y actually decreasing. So that then we can say that these fixed points are stable. If these fixed points are stable, when we can say these fixed points are stable, when the eigenvectors coming from this eigenvalue this matrix is both negative, then we can say this fixed point is stable. Point is stable, and otherwise we can say this point unstable. Now talk about the when the periodic orbit comes. Now if you see that this lambda 1 is a pure imaginary, so lambda 1, suppose lambda is the solution of this equation is plus ai, and lambda 2 is minus ai. If it in principle I will get, I can means anyone could get lambda 1 is pure imaginary, lambda 2 also pure imaginary, then your equation will become epsilon x tilde is epsilon 0 tilde y e to the power minus ai t, and epsilon y tilde is actually e to the power 0 y tilde e to the power plus ait. Now you see this is a, now if this become purely imaginary, you will say that my system is actually oscillating about this state, about the fixed point. About the fixed point, it is actually circulating or it is oscillating. Now why it is oscillating? Because if you see this is since these are the periodic in nature, so uh, after when it become t equal to 0, after when this ai at will become 2 pi, then it will again come to the same point, then that means t will become, time period will become 2 pi by a. So after this much time period, you will see the system is oscillating and the time period of the oscillation is t. So this is the uh, thing that you are asking, that when we can say that the system is oscillating. I know it is not that much clear, because linear stability analysis itself very a topic of a lecture. So that's it. Is it clear a little bit?
Yes, yes, yes.
Okay. So this is the thing. So if I have only two-dimensional uh, space, and if I calculate this matrix, and if I get my eigen values as purely imaginary, then I can say that my system possesses an oscillatory motion. So that's it. We will see that there is an example of Lotka-Volterra equation where this oscillation will come automatically, and if this like eigenvalue become exactly imaginary, it is called neutrally stable. Neutrally stable. Neutrally stable. So let me, so this is too much digression, so let me go to that evolutionary game theory. Now I will, now these concepts will need, these means I will use this language very often, that fixed point, stable fixed point, and unstable fixed point. And whenever I am using fixed point, stable fixed point, and unstable fixed point, I am actually referring to this thing that I have done here. So let me now talk about the evolutionary game theory.
So, I
uh,
mean, can you summarize the important points of this oscillating
exactly,
things again? Yeah.
exactly. So that means if I know that after some point of time this point will come back again here, we can say that system is oscillating, right? So after suppose time t, it is again come back here, t equal to 0 it will be there, and after t equal to t it again come back here, and this repeated motion is repeatedly, going repeatedly, then we can see, we can say that the system is oscillating. Now what I am seeing here through the dynamics, dynamics suggests that yes, it is possible if the, if the my eigenvectors, or maybe you can say like that, my equation of motion is such that equation of motion is such that the solution of the equation motion is comes out to be this, in near about the fixed point, I can say that around this fixed point, around this fixed point, the oscillation is, the pure oscillation will come. And the summarize,
That's okay, but then I
yeah,
mean, what is the role of the eigenvectors here? I mean, why are we including, I mean, those vectors here to
okay,
study
okay,
oscillation?
why are we, so basically why, so then it will be become okay. So you see, when you are just linearize the equation, you will get these two equation, right? And these two equation, it contains one x directional term, one y directional term. So this is still linear, but it is the equation, if you look and want to solve, means it is not, if by looking this equation you cannot tell what is going to happen. Now what we have to do, we have to do a change in the coordinate in such a way that this equation look like exactly this, exactly this. Now I want to change the coordinate by this transformation. That's, is it clear that from, is it clear up to now?
Yes, till here the points are okay,
Huh.
wherein you wrote the two linear
Hmm.
equations for the epsilon x and
Hmm.
for the epsilon y thing.
Hmm. That is clear. Now
Yes.
here I am saying that here the equation is uh, means here the, means here the velocity is in such a way that velocity is okay. So here, okay, that much is clear. That means my x directional velocity is in some such a way that is in, not in x direction, not in y direction, it is some this fashion. Now I want to change my coordinate in such a way, okay, I have to then, I have to show you how linear, do you know about anything about how linear transformation works? How if I rotate a dimension, if I rotate a two-dimensional space, how the coordinate will change? Do you know anything about it?
Yes, yes. So it's okay. So,
Hmm.
like, say, if I consider an eigenvector,
Hmm.
so then the transformation would be like this: that the vector will get multiplied by s by a value
Hmm.
in the same direction only. I mean, the direction will remain unchanged if I say compute the eigenvector of say x. So
No,
I mean
direction
the
will means, since I rotating the space or vice versa, so direction. You may think like that, my direction not changing, but I am
No,
saying that.
I'm only talking about the eigenvectors, not, I mean, not for any specific transformation. So
Hmm.
what is happening in this case? I mean, so what kind of the transformation is being carried out here and by whom?
Here is
Like
the.
say, I could understand
Hmm.
that when you wrote that d epsilon by dt is a collection of these things, that
Hmm.
df by dx, del f by del x,
Hmm.
and del f by del y, and del g by del x,
Hmm.
and del g by del y.
This much is
It
clear.
is it is okay
Ah,
till here. It is okay.
okay. Let me then not going to the evolutionary game theory. Let me talk about little more about the linear stability analysis. Okay, fine. Let this is dx dt is ax plus dy, and dy dt is some cx plus dy. So that means d dt of x, here x means x and y. d dt of x is this is a b c d x. So we can write in this way. Is it clear, right?
So I mean, because you are using the same symbol, say capital X,
Okay,
that is creating trouble here
okay.
actually.
Maybe right. The jet maybe. Maybe jet. Jet. So
Yes, it is okay now.
dz did equal to a b c d jet. Now I want to transform in such a way, means this matrix, I in principle I could transform this in such a way, means I want to rotate my system in such a way that this will become dj tilde dt is equal to lambda 1 0 0 lambda 2 z tilde. Sorry. Is it clear? Means there is in principle there is a transformation. If I do that, I will get a diagonalized version of this matrix, and my this and all the things will change. Is it clear?
So actually, I mean,
Hmm.
why will this happen? I mean, what's the reason behind this? That
Okay.
I can diagonalize, I mean, every matrix or every transformation.
Not every transformation, means in linear algebra you will find that there is a standard method of diagonalization. So if I do the same procedure, I can in principle diagonalize. So that is another topic, means how
Okay,
can,
okay.
there is
Yes,
another
I
topic.
I, I, I understood this thing, but then what is the relation between Z and Z tilde then?
Exactly, z and z tilde will be simple. Z tilde you will find eigen, okay, z tilde and z is nothing but, you can always write z tilde in some a, means z tilde will be some matrix. Okay, let me write that. Z tilde means now we'll get x tilde equal to some constant into x plus some constant into y, and y tilde will be some constant into c1 b1 and c2x plus b2y. This,
Oh yes, I understood. And in this case, the delta one, delta two are the eigenvalues, is it?
in this case,
So delta one, sorry, lambda one and lambda two are the eigenvalues.
lambda 1 and lambda 2 are the eigenvalues, exactly.
Okay, okay,
And
then it's
c and c1 b1 is the eigenvector corresponding to lambda 1, and c2b2 is the eigenvector corresponding to lambda 2.
oh, I see.
This is the
Okay,
thing,
all right.
means, yeah, means this is the thing. If it is clear, then we can proceed
Oh,
further.
yes, yes, it is clear. Then, but then from here,
Hmm.
how did we conclude that this is the oscillating thing and
Yes,
not the fixed point thing?
okay, exactly. So now, since we can, now if it is clear, then now we can write the equation in terms of this. Now we can write this equation in terms of f x tilde equal to, right, let me, this will be d dt of epsa x tilde will be lambda 1 epsa x tilde, and ddt of epsa y tilde equal to lambda 2 epsa y tilde. We could write this from this j tilde means nothing but epsilon x tilde epsilon y tilde. Is it clear?
Yes.
Okay.
Yes. Yes.
Now after that you solve the equation. If you solve the equation, you will get, means if lambda 1 and lambda is pure imaginary, if you solve the equation, you will get epsa x tilde is epsa 0 tilde e to the power I t, means some, suppose lambda 1 equals to ai and lambda 2 equal to minus ai e to the power I a t, and epsa y tilde equal to epsa 0 tilde e to the power minus 8. So that means if this is the solution, that means my system is actually oscillating. Is it clear why it is oscillating?
That point is not clear actually.
Okay, okay. Oscillation means what? Oscillation means after some point my system will attain the same state again and again. Okay, let me see that at t equal to 0, where the my system was, at t equal to 0, my epsilon x tilde at t equal to 0 will be epsilon 0 x tilde, and epsilon y 0 t equal to 0 epsilon 0 y tilde. Now if I get some time after that point, means this oscillation means after some point of time it will again came back to the same point. Let me suppose I will at t equal to t time, it will get back to the same point t t. So let me solve for t. Epsilon x t equal to epsilon 0 x tilde e to the power I a t epsilon x e tilde epsilon 0 y tilde y e to the power I minus a t. Now I am saying that since my system is oscillating, it will came back again in the same position. So that means epsilon x tilde is equal to epsilon 0x. That means if I put it here, I will get epsilon tilde x equal to epsilon 0 tilde x e to the power I a t. So that means e to the power I a t should be 1, and 1 means e to the power I 2 pi. So that means a t, actually this is n, so a t is equal to 2 n pi. So that means t equal to 2 n pi by a, or n into 2 pi a. What is n? N is an integer. So that means at n equal to 1 it will come back, means n equal to 1 means t1 at 2 pi by a time it will come back at the same point. After t2 means n equal to 2 means 2 into 2 pi by a means 2t1. After again spending 2 pi by a time, it will again come back to the same point. So this is actually my system is oscillating. Is it clear?
Yes. 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 It is clear to me now. Yeah. Thanks.
That is the case. Now let's go to this evolutionary game theory. Sorry. Let's go to this evolutionary game theory. Evolutionary game theory. Okay. Now, so with keeping all those thing in my mind, let's go back to our main thing, that is evolutionary game theory. Now, so at the first two lectures we know about what evolution, what does evolution means. uh, Now evolutionary game theory, what is the difference between the evolution that we have seen in the previous lecture and evolutionary game theory is only one thing. So if I go back to these evolution things, then we always consider our fitness. That fitness means number of offspring or the rate of reproduction is constant. But evolutionary game theory introduced that these fitnesses will not be constant. So in evolution, until up to now whatever we studied, the fitness was constant. But from now onward, we will introduce that frequency dependent fitness. And the frequency dependent fitness, if we want to know how the frequency dependent fitness comes, so one of the way is evolutionary game theory. Evolutionary game theory actually are evolutionary dynamics which captures the frequency, which encapsulates the frequency dependent fitness. Now we have to know a little bit about game theory. What is game theory? Then we'll come to how we can introduce this game theoretical concept in evolutionary dynamics, and naturally as an artifact of the using game theory you will find that the frequency dependent fitness automatically came into the picture. And what do you mean by the frequency dependent fitness? We mean that if in the population x is the frequency of some type of individuals, so fitness, its offspring, number of offspring it will produce, it should depend on the frequency. Previously it is not depending on the frequency, it was a constant number a or b. Now I want to introduce it should be depend on the frequency. Now what is game theory? So game theory was first introduced by John von Neumann. He is a mathematician. John von Neumann. John von Neumann and Oscar Morgenstern. Morgenstern. So they actually wrote a book about the game theory, and is the first two chapters of these books is very wrote the book very fantastically. So first two chapters of this book is very interesting to read, how they introduce the concept of game theory. Now apart from that, what is game theory? Game theory means game theory captures the strategic interaction between human beings. They introduce the game theory to mathematize the concept of strategic strategic interaction between two human beings, and what will be those outcome of those strategic interaction. To mathematize those things, they introduce game. So what does mean the strategic interaction? So strategic interaction is nothing but, it is that suppose every human has two options. Now we can choose, suppose we have two option a b. Now there are, yes, a, yes, are you asking something? this is uh, maybe you can mute your mic, maybe, I think, if you're not asking some question. Okay, thank you. So strategic interaction means, suppose there are two individuals are there, and there they have two options. Suppose A and B, and A and B, two options. Strategic interaction means whatever I am doing, I am not getting a payoff only because of that option I am choosing. It also depends on what my other individuals who with whom I am interacting is actually what action he actually choosing. So suppose an example, it is also a kind of, you can model these things with a strategic interaction. Suppose I am teaching a course and some student is learning from the course. So this is a kind of strategic interaction. Now what will be my action could be here, my action could be teach or not teach, and the student's action will be learning or not learning. So one is teachers, from the teacher's perspective, teach or not teach, these two actions are there, and student perspective, to it is learn and not learn. Now the whole outcome, or maybe my payoff also be depend not only on my action. So if I am teaching and no, there is no student who is want to learn, I will get not any payoff. So if I am want to teach, I am giving the action teaching, but no student is there want to learn, so then as a teacher I will not get any payoff, I will get payoff zero. So this is a strategic interaction. The action I am choosing teaching, the payoff I am getting is not depend only on the action I am choosing, it also depend on the which the other, here the students is actually choosing. So this is a example of strategic interaction. So here the means maybe we can write it later. So this is the example of strategic interaction. Now these two gentlemen, John von Neumann and Oscar Morgenstern, what they did in their book, they mathematized how could we write a mathematical formalism for what will be the outcome when a teacher student interact, what should be the, what means in which way they should act such a way that they both will get maximum payoff, maximize their payoff. This is the concept of game theory. Now again in this picture there is another gentleman came, whose name is John Nash, who's a John Nash. And John Nash, during his PhD in mathematics in Princeton University, came means with an idea or thesis, means his thesis published in a single two-page paper, and that paper brings him Nobel Prize, and that paper was about the Nash equilibrium. And he give an idea that you can write the game theory and there may be possibly many solution exist, but he give an equilibrium solution which exists for all kind of game, that is called the Nash equilibrium. Nash equilibrium, Nash equilibrium, in short Nash. And Nash, it means he is okay. So that is um, the game theoretic part. So in game theory you can formalize a strategic interaction, and then after formalize the strategic interaction you will always find a equilibrium which is called Nash equilibrium, and that Nash equilibrium means is means if any two human beings, or in technical term if any two rational individuals play that game, that means are doing that strategic interaction, they will always go toward this Nash equilibrium. That is done. Okay.
I have a query here
Okay.
that is it necessary that if, say, multiple people are interacting with one another,
Exactly.
So
strategy.
then the things will always reach to an equilibrium kind of the thing wherein things will always reach to an equilibrium kind of the thing wherein no one is getting benefited more if he deviates from something.
Yeah, yeah, we will see that the definition of Nash equilibrium exactly. I'm just telling you. Yeah, you are right that there will be, means Nash equilibrium in formally when we introduce the mathematically the idea of Nash equilibrium, you will see the definition of the Nash equilibrium. There we can see that formally it means let me give you formal definition. Formally means Nash equilibrium means exactly whatever you are pointing towards. That Nash equilibrium means outcome. Suppose action A and B. If anyone unilaterally deviate from this outcome, he cannot get more payoff than whatever he is getting at remaining at Nash equilibrium. So no one has any incentive to unilaterally deviate it from the Nash equilibrium. That is the definition of the Nash equilibrium. And for the game, for the strategic interaction, always more than two people, means at least two people is required. Means
But then, what is the need of the game theory, and why are we moving away from the differential equations? The differential equations are working so very well for us, and since last 2 days we were
huh,
solving these equations only. Then all of a sudden, why did we move to this, the interaction among the people and this game theory stuff?
exactly. That was what I am motivating in the first. So uh, so in the previous class we are seeing that fitness is constant, reproduction is at a constant rate, reproduce at a constant rate. Now after that we want to introduce another concept. So it is called the frequency dependent fitness. So these frequency dependent fitness will automatically came into the population, means when we see the population level uh, thing, means everyone is not that I means any individual is reproducing not by himself or herself, he always interacting with some other individual and reproduces. So this will be the case. So that will naturally brings this game theory into the picture.
But then we could have introduced another variable, say the
Hmm.
fitness,
Huh.
in the differential equation, wherein the
Exactly.
fitness is also varying with the time, and we could have come up with the non-differential equation, non-linear differential equations then.
Exactly.
But what is the need of, I mean, coming to this game theory thing?
Okay.
All of a sudden,
Need
a new
of
idea or the
basically.
new concept.
Okay. Exactly. So this is that. So uh, here game theory means what? In a sense that it is actually maximizing my payoff, maximizing everyone payoffs. And what natural selection says that those behavior or trait will be selected which have the in the fitness term which will be the highest fitness. The fittest individuals, fittest behavior will be selected. So these two means by hearing these two, one is maximizing the payoff and one is maximizing fitness. If we connect by somehow this fitness by fitness with this payoff, will automatically get the natural selection. So that's why we want to introduce the game theory. One, the first is that. And another thing, in the previous case there is no way to capture the interaction term. Suppose I am, means suppose there are A type of individuals and there are B type of individuals. But in the previous case, there means there is in principle we can write without using of game theory, but we want to write this equation. So if when A interact with B, how much fitness they get. So since there is means whenever you want to tries to do that, the game theoretic language will automatically come into the picture. So we will see that thing. You wait for a moment, so you will see that where the
Yes.
game theory will automatically come.
Okay. Okay. And I could not understand one term which you used, that payoff thing. So
Hmm.
what is that?
payoff means whatever I get out of interaction. So that I am telling you here by that example. So suppose uh, payoff for classical game theory. Let's be crystal clear about that because it will put. So payoff in classical game theory is the satisfaction I am getting. So suppose I am teaching and there is no uh, student wants to learn that subject, so then there will be not meaning, there is no meaning of teaching. So that means what payoff I am getting? I am payoff, I am getting zero payoff, means I am not at all satisfied by teaching that subject. So in classical game theory, the payoff means the satisfaction I am getting. But
Uh,
okay,
will this be a numerical value?
there is a numerical, there is a numerical means, yeah, this is a theoretical problem. Now if you if I stay in the realm of von Neumann, or means von Neumann utility theory, means von Neumann payoff theory, or utility means the same as the payoff. The utility and payoff I am using synonymously, but these two are the same thing for classical game theory, not for evolutionary game theory. For classical theory, classical game theory means game theory, and up to now whatever game theory we are talking about is classical game theory. And for this, if I stay in the regime of utility, means expected utility theory, or von Neumann Morgenstern utility theory, we can write this satisfaction number. Why? Because uh, for me, means if I know, if someone knows, they, means the logic is this way. So suppose there is two action, teaching and non-teaching. So if I know that what I like, teaching or not teaching. So suppose if I like teaching, uh, teaching over not teaching. So then we can represent by my satisfaction by a real number, which is suppose teaching is 1 and 0. The exact numerical value does not mean anything here. Only the meaning associated with the numbers is the ordinal relationship, means whether I like teaching over non-teaching. So that means I represent the teaching by 5 and or 1, and non-teaching by 0. It doesn't matter if I represent the teaching by 1000 and this by 1001. It still remain, it's still telling the idea that I prefer teaching over not teaching. The number only captures this much for classical
Oh,
game theory.
oh, okay. So later on, like say, I cannot talk about taking the average of the two value kind of the thing, because then the ordinal relation will hold and there won't be any meaning of the average or the square root kind of the thing.
Exactly. Whatever you are talking about, it is exactly same, but there is a little bit catch here. So for, let me, this is true. Whatever you are talking about, it is true. But since you are mentioning about average, so suppose there could be a situation, I have to choose between these two situations. Suppose with probability x, I could teach, with probability 1 minus x, I am not teaching. There may be some situation happens in my life that with probability some, when non-teaching happen, and if I still like this event, with y probability I am getting, means I have means there is a possibility of teaching and 1 minus y is not teaching. So there is a now two different kind of situation. Now here with x probability I am teaching, and with 1 minus x probability, means if we say in a one day in some fraction of time, means or with some probability I am teaching and some probability I am not teaching. And here there will be different probability of teaching and non, there will be a different probability of not teaching. Now between these two uncertain event, which one I prefer? I may prefer this one, and I may prefer also this one. But if I stay in the axioms of the von Neumann Morgenstern utility, I will always say there exists a payoff or a utility for this uncertain event that could be represented by this, that x into the number I suppose number I written there, x into 1 plus 1 minus x into suppose 0, that will be my average utility or expected utility from that outcome. Here again this number doesn't mean, but if I stay in the regime of expected utility theory, we can write, means it's a totally mathematical concept. uh, means there is no physical aspect of about this, but uh, this is the thing we can write expected utility if the situation is uncertain.
Yes, I understood. And so actually the values assigned here
Huh.
do not matter. So instead of 1 and 0, we
Huh.
could have taken say 100 and
Huh.
say 500
Huh.
kind of the thing also.
Yeah.
Okay, okay. And who assigns these values, by the way? I mean, who
Ex-
assigns the values of the payoff?
exactly, the you are asking the right question. So these values for classical game theory, these values are assigned by the analyst. Means here I am, since I am analyzing the situation, so I am assigning the value for calculating the situation, for calculating the situation. Means I cannot say there exists a value which is assigning by that individual. I can only observe, means since I want to model the system, so I can only observe, suppose a individual who is liking tea over coffee, he is not giving a value to tea and coffee. Here the individual who want to analyze the situation, he actually giving these values. Is it clear?
Okay, yes, I understood. Yeah, thanks. Yeah.
Yeah. So that is the thing of classical game theory. So that further more, this is the thing for classical game theory. Now will now let me write it, classical game theory here. This is classical game theory. Now let me talk about evolutionary game theory. Let me talk about evolutionary game theory. Evolutionary game theory. Now, this the concept of evolutionary game theory is the concept of game theory uh, used in evolutionary dynamics, done by the first William Hamiltonian and Robert Rivers, who used the game theory concept in evolutionary dynamics. Now, the first gentleman who used the techniques of game theory exactly in evolutionary sense is John Maynard Smith and George Price in evolutionary biology. So, as we are talking about in traditional or classical game theory, what people are after is, so if I means suppose in classical game theory here, so I am assuming that I want to, means teachers want to maximize his payoff and student also maximizes his payoff. Now if I assume that teachers means student, if I assume that student maximizes his or her payoff, and in that, if I assume that in that case, what should I do? So that is the thing of the classical game theory, and this thing is called, means the thinking is needed. I assuming what I should choose if the student is not wanting to learn. What should I choose that will maximize my payoff? And I also think that what the student will choose if she also thinks that I want to maximize my payoff. So what will be by maximizing, by analyzing this concept, by analyzing this situation, where our means where we will reach. So that type of thing is going on in classical game theory. So the concept is called the rationality. So here the every individuals who are playing the game have to have some rational mind, or it is called rationality. But what John Maynard Smith and George Price tells, that without this rationality, without thinking about that, that I am going to maximize my payoff, is there is a population, and population can play a game without thinking about the rationality. Suppose there are individuals in a population who are not rational at all, but is it possible that we can write a dynamics, or we can represent their dynamics by game theory? That type of question asked by the Maynard Smith. Now and he write down, and this the thing, then in evolutionary game theory we will not ask about that the uh, individuals are rational. In evolutionary game theory, individuals are not rational. Indivi- individuals are not rationals. Individuals are not rational. These individuals are is called myopic individuals, and they only reproduce. Now one thing is introduced in the reproduction part. So reproduce, they don't reproduce by themselves, means suppose there is an individual A is not reproducing A plus A, but to reproduce another A, she has to interact with some other individual B. Then maybe she can reproduce a individual with some rate, suppose some alpha rate. So here it is, as it means as if these two individuals are interacting with each other and reproducing another A individual, or maybe another B individual with another rate. So that thing is needed here. That is called the interaction in evolutionary game theory. And
So I have a query here.
okay.
So, what's the difference in between the classical game theory and the evolutionary one? So, is this the only difference of the rationality that in the classical game theory, all the participants are rational and they are trying to
Hmm.
maximize
Hmm.
something,
Hmm.
and in the evolutionary game theory, the participants are not rational and then they are trying to reproduce?
Yeah, yeah, that is the one. And the second thing I am coming, and the previous one, what was the payoff? Payoff was my satisfaction, my utility. This is only the subjective things. But in classical game theory, the payoffs or the utility is the subjective things. No objective thing is there. But in evolutionary game theory, what the payoff means? Payoff is payoff is equal to the number of offsprings they are getting from a interaction. So suppose here a number of offsprings, or you can say the rate of reproduction. Rate of reproduction is the payoff here in evolutionary game theory, not the subjective satisfaction, but here the objective number, the rate of reproduction or the number of offspring that the individual, this A individual is getting while interacting with B individual, that will characterize by the payoff. This is the main differences here. Is it clear?
Yes, yes,
Okay.
yes.
So now this is the evolutionary game theory. uh, Now we will go step by step. Now let me give you an example where you can see that how that frequency dependent fitness makes a sense. So suppose there are two phenotypes, A and B. Two phenotypes are there. A phenotypes, here phenotypes is nothing but two types. Here one have one characteristics, A have one characteristics, B have other characteristics. Suppose B may be blue hair, B may be black hair, and A may be black hair, B may be red hair. These two are called the phenotypes, or maybe simply types. there are two phenotypes of some bacteria. Suppose there one has no flagellum or it cannot move. Suppose A cannot move and B can move from one place to another place. So since A cannot move and B can move, so B has to incur some cost, but since B can move, so that's why B will get also a benefit. So that benefit, if I write that benefit in terms of fitness, suppose means B has a fitness higher than A. In normal case, suppose B has a fitness 1.1 and A has a fitness 1. Now this is well and good, but you consider one situation. Suppose all the individuals are A and one B individuals are there. Now in this case, B will get much more advantageous because it will not get, means there will be no one which will be also moving with him, moving with her or moving with it, maybe moving with it. So that's why you will get lot of benefits, enjoy the benefits. But if instead of this situation, suppose this situation occurs, everyone moves, then it may be a case that it may be a case that these individuals got stuck in somewhere. That means when all the individuals or near means most of the individuals are B type, maybe then these individuals not get that much benefit that it was getting when the all the most of the individuals was A. So that means in principle the fitness should depend on the depend on the frequency of that individuals which are present in the population. So let me, so as you are suggesting that, as if I stay in the regime of the previous lectures, so we could write in principle an equation which is, suppose xa dot will be xa, and here fa, fitness of fa, here fitness of fa and fitness of fb, previously it was constant, now it is depend on this frequency of xa and xb. So xa and xb minus 5. So as you are suggesting, in principle we should write a equation which look like this to encapture the frequency dependent fitness. Xb dot equal to xb xa comma xb minus 5. So now since the size of the population is fixed, that means xa xb equal to 1, in place of two equation we can write one equation. Let me write xa is equal to x and xb equal to 1 minus x, then this will become x dot x into 1 minus x, and this will be fa x minus fb x. This will be my equation. Now again, so there will be how much fixed point, how many fixed points are there? 1 x equal to 0 fixed points, 2 x equal to 1, and 3 x equal to x star. So how will get x equal to x star? By solving fa x star minus fb x star is equal to 0. These are the fixed points. By now using linear stability analysis means nothing. I have to calculate the first derivative of the velocity, means dx of x dot, or this function x 1 minus x fa x minus fbx at every fixed point to check whether the fixed point is stable or not. So if I check at x equal to 0, you will find that this will become fa0 minus fb0. So that means if fa0 is less than fb0, means the fitness of the a at point 0 is less than fitness of the b at point 0, then the x equal to 0 is a stable fixed point. If it is the case, then it is a stable fixed point. And similarly, you will see this is 1, is 2, at x equal to 1, you will find the condition if this other should be other way around, if a is greater than fb1, then x equal to 1 is stable. And the third one, you will find that if x equal to x star, that if fa prime x star is less than fb prime x star, then this internal fixed point is stable. So this is the thing. So whatever we learned the previous class, if we blindly applied those things here, we will get simply these things. Now where these evolutionary games came here. So let me introduce a game which is called two-player games. Two players, two-player games. Okay. Two-player games means there are two players. Two-player symmetric game means not about complicate the situation much, but in technical word it is called symmetric game. So player 1 and player 2. Suppose player 1 has a player 2 has a 2 action, player has 1 has 2 actions. AB. Suppose if player here, if the player 1, these A and B are the actions. Okay. If player A strategically interact with player 2, suppose here it is the action of the teacher, here the action of the student. So if the teacher takes the action and the student takes the action, then the teachers will get some payoff. That payoff is A, and the student also will get some payoff, that will be suppose A again. And similarly, if A interacts with B, then player 1 will get some payoff B, and here B interact with A will get some payoff C, and B interact with B will get some payoff D. And since similar situation happening here, B interacts with B, it is also get D. Now here A interacts with B, what A will get? B. But B, player 2 strategy is B, but my action is A, then what I will get? C, because here I have written that if the player 1 plays action B against the A, it will get C. So this will be the payoff matrix. Is it clear? Payoff matrix.
Yes, I mean, it is not clear to me.
Okay.
If you can explain.
Yeah. It is the everything in this course. So let me take a little bit time now. So in principle, this situation could happen. So there are two players. So suppose there are two players. So there are four possibility happen. So player 1 takes A, player 2 takes B. So for that they both will get something, and again player 1 takes A, player B takes B. For that he also gets something. Player B takes player 1 takes the action A and player B takes the action, player 2 takes the action, suppose A, and these four things would here.
Is this possible that both the players have different actions? Like here, we are taking the
Huh.
same actions for A as well as for the
Yeah,
B.
yeah, it means for the game of the student teacher game, you means here the two roles are there. Teachers has two action, teaching or not teaching. The student has two action, learning or not learning. So both different kind of action is possible. That is called the
Okay,
asymmetric game. But we will not go towards that asymmetric game, we will stay at the symmetric game.
okay, okay.
Yeah. So I am saying that in this situation, both players, since both players playing action A, both players getting the pay of A and A. A gets the pay of A, and the second one is the pay of the player 2. He is also getting the pay of A. Now the situation comes where AB. Here I am playing A and you are playing B. So I will get some pay of, suppose I am getting a pay of B. So that means I am writing here in the first elements represent the payoff of the player 1. So player 1 gets the payoff B, and the player 2 whose action was B is getting the payoff C. Suppose I am supposing that he is getting C. A, this is the first player payoff, player 1, and this is player 2. That is the case. Until now it is clear.
Yes, it is clear to
Okay.
me.
Then when I am playing B against action A, that is the similar situation that you are playing B against uh, when I am playing A. So this will be the same situation. Only the player changes. So I am, since I am regime in the symmetric game. So that means I will get the payoff what you will get when I was playing A. So that means when I will play B, you will, when I will play B and you will play A, I will get the same payoff as when when you you are playing B and I am playing A. That I am, then the B player, the second player gets C here. Similarly, the first player should get C here, and the other player should get B. Now, yeah.
Yes, yes, it is clear.
Okay. Now, if both players play B, action B, they will get some other D and T. This is the thing. This is the payoff matrix. Now, we let me write in this way. So, now let's talk about. So, what will be the? This is the payoff. Now, what is the? Okay. This is the thing. Now, if I want to explain the same thing in the evolutionary game theory, language of evolutionary game theory, I will say in this way. This is the classical game theory. So when one A types of individual, suppose we have a population, there are only two phenotypes are there, one is A and another is B. When A type of individuals interact with B types of individuals, they will get a
So, what this phenotype thing is?
phenotype.
Phenotype.
Means previous, in the previous class, the phenotypes means two types of behavior. Means one has means, suppose here, means in this example, previous example, one has a flagellum, means one can move, one cannot move. So these two are the phenotypes. So phenotype means the behavior.
Okay,
Two
okay.
kinds of behavior are there. So if one types or maybe phenotypes or types, I am using loosely these words, that phenotypes, types and genotypes, all these things mean similar, they means the behavior. So A, when a types of individuals interact with the B type of individuals, these A type individuals get, suppose A type individual reproduce another A type individual, so these two individual will be there, but another A type of individual will created with rate, with reproduction rate, with reproduction rate A. Now here I will say that A getting chance of reproduction herself with probability A or with reproduction rate A. So this A is the payoff for this individual A, the phenotype A. And similarly, when this could also generate A plus B in this interaction, that it may also happens that sometimes the B also get chance of reproduction herself, reproduce herself with rate, with rate, sorry I am using the this wrong way, so let me say here this way. This reproduction rate should be when A is interacting with B, its payoff is B, so the reproduction rate should be B. And when A interacting with B, the reproduction rate of the B, that means one A B individual produced with probability, is C. Is it clear now what does this payoff element means in evolutionary game theory?
Actually, it is not that clear because when
Okay.
A and B are interacting,
Huh.
so it is being shown like A and B are interacting
Hmm.
and then they are producing A.
A.
And in the second case, A and B are interacting and then they are producing B.
Exactly.
So now in the classical game theory,
Yeah.
when A and B interact, can you go slightly, can you scroll it up,
Yeah.
please?
Yeah.
Yes. So when A and B interact
Hmm.
and producing A is, so how to represent, I mean, this payoff by small a, by small b,
Small b.
because A is interacting with B, but then what payoff B gets? So so what payoff B gets is small c. So therefore, in the second case, this value will become C.
Yeah.
And when A interacts with B and what benefits A get
Hmm.
is B, so therefore B becomes value here in the first. Is this the case?
Yes. Yes. This is the case.
Okay.
The
Yes.
reproduction rate is B here, and here the reproduction rate is C. That is the case basically. That is the meaning of the this payoff element in terms of evolutionary game theory. So this is the thing. Now how can I calculate the fitness here? I have say you that I have said it that the frequency dependent selection will automatically came into the picture. Now suppose I have an infinite population, infinite population, and individuals are interacting each other randomly. They are interacting randomly. Then what is the probability that A will, suppose, and this is the thing, and suppose another thing, the frequency of A type in the population is X. Then what is the probability, that means the frequency of B type will be 1 minus X. Now if I ask the question, what is the probability that one A type individual will interact with another A type individuals? The probability will be simply X, since the probability that A type individuals find another A type individuals, since the frequency of the population is X, So the probability that A type individual will find another A type individual, the probability will be x. The probability of this happening is x, and in this time they will reproduce another A type individual with reproduction rate A, and the probability that this process happens, so one A type individuals randomly interact with a B type individuals, what will be the probability of that? The probability of that will be probability of 1 minus x, and in this time the A type individuals get the reproduction rate will be B, and they will get a benefit A plus A plus sorry B plus A. So that means what will be the, if I take randomly one A individual, what will be its fitness on average? Its fitness will be, the fitness of A should be the average fitness, so x into A plus 1 minus x into B, because with x probability it will get A fitness, and with 1 minus x probability it will get B fitness. Is it clear that what is the meaning of fitness here?
Yes, yes, it is.
Okay. So similarly, we can write the fitness of the f of b, that will be x into, similarly, that x into c into x into c plus 1 minus x into d. So let me write this way, it will be clearer. So then so one b type individuals meet with a type individual, and they will reproduce at a rate c, and b type individuals get chance to reproduce another b type individuals. So the process of b type individual finding another a type individual is x, and b type individuals finding another b type individuals, the probability will be 1 minus x, and they will reproduce at a rate d, so b plus b, they produce a b. So that means the fitness of the FB will be, with x probability they will reproducing at a rate c, with 1 minus x probability they are reproducing a d. So that's it, you get the fitness actually depend on the frequency. It automatically, it's automatically product of this game theoretical interaction. I do not assuming any other thing, but it automatically came that the fitness should be depend on the frequency if they interacting in the game theoretic manner. Now I can simply write my equation there. From this I can simply write this equation, since I know fa and I know fb, so I simply write this equation, x dot equal to x 1 minus x fa x minus fb x. So this will be x into 1 minus x, this will be fa x is xa plus 1 minus xb minus xc minus 1 minus xd. So if I simplify it, it will become 1 minus x, this will simplify it, it will become a minus b minus c plus dx plus b minus d. So these called the replicated equation. uh, so this is okay. So let me stop today's lecture in this at this moment, and in the next lecture I will talk about the solution of this equation in terms of evolution, in terms of linear stability analysis, and also I will corresponding to the outcome, to the game theoretical outcome, how I will I will say about how you can see that what the game theoretic outcomes are saying the same thing we can see from these equations. So these are the things we will teach in the next class, and all the other things that in the evolutionary game theory, in the technical terms of Nash equilibrium, and what the Nash equilibrium means in the evolutionary sense, and in the evolutionary, for the evolutionary concept we need to know another concept which similar to Nash equilibrium, is called the evolutionary stable strategies, evolutionarily stable strategy. So those things we will see in the next class. So that's it for the today. So if there is any question you can ask me.
Yeah, so I have two, three
Hmm.
questions here.
Hmm.
So the first question is that I mean, in the
Hmm.
game theory,
Huh.
do we? I mean, do I mean, in game theory, the population interact only once or multiple times? I mean, is it possible that capital A and capital B are interacting,
Hmm.
say, or are having games multiple
Yeah,
rounds?
exactly. In multiple rounds game, exactly. They could interact multiple time. You are saying no. There could be, okay. You can think in this way. You are asking the one could be the thing that repeated interaction would be there. So I will, that will be a separate topic. I will cover that thing in this course. So after this evolutionary game theory, I will jump into that, that if they are interacting multiple times, what will be happening. So that will, I will do that. So first thing is that, and the second thing is that here also the sense of repeated interaction is captured by the way that when I am introducing the probability, so I am saying that at once, or in one time, I am seeing that someone is interacting and reproducing, and the second time also they will do the same thing again and again. That's why I am writing the equation. So they are not reproducing only once and stopping there. They are reproducing, they are interacting with each other and reproducing. They are interacting with each other and reproducing. That's why we got this time evolution equation. So
Yes,
uh,
yes. No, I understood. Yeah.
there are two part. One part I will, means there is a separate part, means if I and you, means in classical game theory, if I and you interact for once, so only one class is there. So I and you interact for only once. That is a one type of game theory where the individual interacts only once. And it could happen, so no, we know that we are not meeting only for once, we have to meet multiple times. So in for that case, this is a separate case that I will cover in this lecture, which is called the repeated interaction game. So that is a topic
Okay.
of this
Okay.
course.
Okay. And
Hmm.
which software or the framework, I mean, people usually use to simulate, I mean, these
Sorry.
game theoretic, I mean, scenarios?
Okay, game theory oh, this is a very nice question. That means in any software, means in anywhere you can calculate the Nash equilibrium. So if you know the definition of the, if you know the definition of the Nash equilibrium, you can calculate the Nash equilibrium. But uh, in principle the Nash equilibrium is there, but the problem is if the number of individuals is interacting is become large. So suppose here we are only interacting two individuals, so calculating the Nash equilibrium is very simple. But when the number of individuals become larger, this problem become NP hard, means I don't know the exact term of the NP hard means, but it does, it means technically it, the by finding the Nash equilibrium for any number of individuals are interacting, any number of strategic interaction, is actually very hard problem. Numerically, means when the number of individuals get maybe 100 or more, maybe you could not, in principle it is there, theoretically it is there, but by using numerics, you, there will be not any sufficient algorithm by which you can calculate the Nash equilibrium.
Okay. And yeah, so then would you be mailing, I mean, emailing these notes? And so where are you uploading these notes? I mean, would you be
This,
sending these notes through email or what?
okay, I will maybe I do one thing. I will upload the notes in my drive, and I will share you the drive link.
Okay, that would be really helpful.
Okay.
Thank you so very much. So tomorrow the class would be at the same time.
Yeah. Tomorrow the
Okay.
same.
Yeah.
Thank you for joining.
Thank you. Bye. Yeah.
Bye.
Bye.